Okay, so thanks to Azim and Stefan for organizing another great conference. I also want to do something ill-advised and thank my discussant, Frank, ahead of time, which may be not a good strategy, but he's filling in on short notice for someone else, so thank you for disrupting his week to do that for me. Okay, so this paper, what's the motivation of this paper? So it's motivated off the observation that in a lot of econometric models that are nonlinear, parametric distributional assumptions drive identification. So what I'm thinking of for nonlinear models are things like binary choice or more general discrete choice models, sample selection models, models for counts, or duration data, things like these. Okay, so a natural question that arises is what is the extent to which these assumptions, which I'm thinking of things like errors being normal, errors being logistic, things like that. So what's the extent to which these assumptions drive empirical conclusions? Why is that an important question? Well, typically we view these assumptions as being non-economic. They serve an important part in the point identification results that usually arise in these models, but they're not motivated by any specific economic theory per se. Okay, so that leads to the question of what we can identify without making these types of assumptions. There's two approaches that people have taken to look at this question. I'm not the first person to think about this. The one that's seen the most use in the literature in the past 20, 30 years is to look for other non-parametric type of assumptions that you can use to obtain point identification once you relax these distributional assumptions, okay? So there's been a lot of fruitful results from that literature. In nonlinear models, it typically involves conditions that look something like a large support condition, meaning that you have a variable that has a lot of variation that's exogenous. And that can sometimes be a difficult condition to credibly argue as being satisfied in actual applications. Okay, so I'm not going to do the first approach. In this approach, I'm going to do something different in this paper. I'm going to take a second approach, which is to find what the identified set is, ideally the sharp identified set, without using these parametric distributional assumptions, okay? So the difficulty here is that this is often technically sort of a challenging problem in complex semi-parametric models. All right, so I'm going to do the second approach. And in particular, the contribution of this paper, I'm going to show you a new general argument for characterizing sharp identified sets. It's called partial identification by extending subdistribution. It has a tasty acronym called PIES. It's based on copula theory with the subdistributions in the title of this paper and in what I'm referring to as the method. They're a generalization of subcopulas, so if you've seen copula theory, maybe that'll ring a bell. I'll talk about that a little bit more later. And the characterizations of these sharp identified sets are low-level and tractable, and they often reduce to solving linear programming problems. Okay? So the relevance to empirical work, let me give you an example. So suppose that we want to determine the average treatment effect of an endogenous binary variable y2 on some outcome y1. So this is a common problem in empirical work. A couple of examples of papers that have done things like this are Angerson and Evans, who are looking at the effect of childbearing on female labor force participation, and Altanji and co-authors, it's Elder and Tabor, who are looking at the effect of Catholic high schools on various measures of high school performance, so such as like, did you graduate or not, okay? So those are binary type of situations. Now, the first thing you might consider doing if you've taken econometrics classes of a certain variety is you might consider doing a bivariate probit model of a Heckman 78 type of thing. So in this type of model, you'd have two threshold crossing equations, one for y1, one for y2. And you have a couple of error terms, and you assume those error terms are independent of x and z, and supposedly you'd have a good economic reason for doing so. But then you'd also assume that u1 and u2 are normal. Okay? And why would you do that? Well, it's important for the identification, but there's not really a very good economic reason to do that. Now, I shouldn't say it's arbitrary. It's not arbitrary. It's done for a good technical reason, but it's non-economic in motivation. Okay. So in recent years, you've seen a response to these types of models, which is primarily motivated by an aversion to this type of bivariate normality assumption. And the response sometimes leads people to do things like use two-stage least squares for binary outcomes and binary endogenous variables, and that's somewhat difficult to justify as a rigorous practice. It's maybe easier to justify through expediency or other types of arguments, but sort of formal technical foundation, it's a difficult position to maintain. Okay, so in light of both of these types of viewpoints, what I want to do is figure out what we can say about the average treatment effect if we maintain all of the Heckman 78 type of model, but we drop the normality assumption. Okay, then what is left over and what is the empirical content of this model? And when I do so without adding any additional assumptions, so without having things like large support, under which various assumptions we could maybe get point identification, but I don't want to assume that we have any of that type of variation in the data. Okay, so that's the empirical motivation. What I'm going to show to you today is not ready for prime time, so it's there's a lot of details that remain on implementation, but characterizing the identified set in this type of model is a first step. So if you agree with me that this motivation is that getting rid of the normality assumption is an important motivation, well, this is a first step, what I'm going to show you to doing that. Okay? Okay, so how does the argument work? I should mention it's applicable to a broad range of models, but I'm only going to talk about binary response models today to keep notation as simple as possible. So my notation for a binary response model, I have an outcome y that's binary. It's determined as 1 when some unobservable u is bigger than g of x. G is some function that we might parameterize. It might be linear index function, something like that. X are observed explanatory variables. U is going to be distributed like f, conditional on x. Okay, so this f function is going to be an important part of what I'm talking about. It's the distribution function of f of u, conditional on x. And like I said, I'm going to focus on not parameterizing this function and seeing what we can still say about identification in this model. Okay, so a couple of definitions which are standard. Admissible parameters are parameters we are going to entertain as being possible, so the ones we don't assume away a priori. So the structural function g is going to live in g dagger, and f is going to live in f dagger. And the identified set is then going to be the set of all admissible structural functions g, the identified set for g, is going to be the set of all admissible structural functions g that could have generated the distribution of y given x that we saw in the data, okay, for some distribution of the unobservables u. Okay, so mathematically what this means, well, here we have the distribution of y given x that we saw in the data. This is the probability when u is distributed like f, that was the case. And so if you just write that out, it's f composed with g of x, conditional on x. Okay, so really simple. All right, so the observation of this paper and the main contribution starts from the observation that this is an infinite dimensional existence problem. So if we care about the identified set for g, we want to know whether there exists some f for which this is true. But f is an infinite dimensional object, right? It's a distribution function. It's a complicated thing. I don't know how to search over an infinite dimensional space, so I don't know how to solve this existence problem. Right? The argument that I'm going to show you is going to reduce this to a finite dimensional problem. In particular, one finite dimensional problem for each point of support of x. Okay? It's going to be a sharp characterization. Now the sharpness sort of in practice requires that you have a finite support for x, although in the data I would argue we always have a finite support for x, so I'm not too concerned about that. And if you are concerned about that, well, I can tell you that you can get an arbitrarily sharp outer set if you want by using as many of these support points as you have. Okay, so how does the argument go? It's based off of a definition, which is my definition, but I think you'll agree makes sense as a definition of a subdistribution. So what is a subdistribution? Think of it as being a distribution function that's not defined everywhere. Okay? So a distribution function satisfies three properties, a one-dimensional distribution function. At negative infinity, it's 0. At positive infinity, it's 1. And it's weakly increasing. Okay? So it's an object that should be familiar to you. The subdistribution just says instead of having f be defined everywhere, it's only defined on some proper subset of the entire real line. Okay? So this proper subset is going to be called u in my notation. And from that definition, you can see pretty quickly that any one-dimensional subdistribution can be extended to a distribution function. I say that's obvious. Why is it obvious? Well, if you look at a picture, so here's a picture. The picture shows the set U that I'm thinking of f bar as being defined on in bold. So bold here is the script U set. And the subdistribution function is represented by the bold dots and lines and stuff. So you can see that if I had a subdistribution function, which is just like a distribution function but not defined everywhere, I could easily sort of interpolate and extend and to get a distribution function, right? So not rocket science. Okay. So why is that relevant to this partial identification problem that I'm looking at? It turns out that instead of finding a distribution function to figure out whether G is in the identified set or not, you can find a subdistribution function. So you can greatly reduce the dimension of the problem. So here's a claim that formalizes that. So suppose I fix some value of G that's admissible, and I want to know whether it's in the identified set or not. And suppose for the time being that I assume that I'm not restricting the distribution function. Now that's a trivial problem because we know we're not going to get anything back for identification if we don't restrict the distribution to the unobservables at all. But just bear with me because the argument's going to be the same when we start restricting it. Okay? So I'm going to define a set script U sub x of G, which is going to have 3 points in it right now. It's going to have G of x, remember G is fixed, and it's going to have positive and negative infinity. Okay, and then the claim is really simple. It's that G is in the identified set if and only if there exist subdistributions defined on this script U set for which the observational equivalence condition holds when we replace f by f bar. Okay? Why is that true? It's like a two-line obvious proof. One direction is super obvious. If we know G is in the identified set, then there exist distribution functions that rationalize it, right? They give us back the observed distribution that we saw. If we restrict those distributions, then just by definition, they're subdistributions. So one way is immediate from the definition. The other way uses this third bullet point up here, that every subdistribution can be extended to a distribution function. So if we find these subdistributions that satisfy the observational equivalence condition, then using an argument like this, we extend them back to distribution functions. And they still satisfy this observational equivalence condition because they're an extension. And so therefore, G is an identified set. Okay, so this is an if and only if characterization, which means this is a sharp characterization of the identified set. Now, importantly to this problem, there's many sharp characterizations of the identified set that you can come up with, and many of them are not very useful because they're not easy to sort of get your head around or implement practically. This one is, and in particular, it's equivalent to solving a finite linear system. Okay, so explicitly, what does that finite linear system look like? It looks like this. So the variables of the system are these f bar variables. They're indexed by U, okay? But the variables we care about are f bar. And they're going to satisfy these linear conditions, some of which are trivial, but I'm putting them up here for sort of clarity. So the observational equivalence condition is a linear restriction of a very simple form. So are the three properties of a subdistribution, right? With the important one being this monotonicity one, really. I mean, these are, you could just get rid of this, but these are the important ones. All right? So it's a linear system. Now, I said that problem was trivial because I didn't restrict the space of distributions we were considering. And so, of course, you'd expect that you wouldn't get any identifying content in a model like this, and that's true. I did that for simplicity. Suppose now that we restrict the admissible set of distributions that we're going to consider to being only those that have median 0. So if you're familiar with like the Chuck-Miansky semi-parametric binary response work, these are the assumptions he works under. So the estimator that arises from that work is called maximum score, so you might be familiar with that name. So we know that the content of this model is not trivial anymore. How do we adjust this argument to incorporate that knowledge, that a priori knowledge that the distribution is median 0? Well, we just add a condition, a linear condition. Just tack it on. Now to do that, we have to add 0 to the set that we're considering, so this U set. Right? So we increase the number of variables that we have, but then we just add another constraint, that f bar at 0 is equal to 1/2. Our argument goes through exactly the same, right? If there's a subdistribution that satisfies all these conditions, I extend it back to a distribution function. It still satisfies all these conditions, and so then G is in the identified set. It's exactly the same argument. And you can take this argument and generalize it substantially more. In this form right here, I mean, already this is a simple computational method to find the identified set for the index function. in a semi-parametric binary response model. So again, there's the Mansky citation. Joel Horowitz talked about this in his monograph. And Tatiana Komarova also developed a way to do this that's different for this particular type of model. Okay, so this by itself is not a contribution, but I can extend this in many directions. So I can impose many different assumptions on the admissible set of distributions, which can help narrow the identified set. I can apply this to many different types of models. And importantly, in my view, I can also extend this argument to find sharp identified sets for the average treatment effect. So I'll show you how to do that now. Why would you want to do that? Well, to some people it might be obvious, some people not. If you read recent work by people of a more applied persuasion, they would frequently argue that this index function g, so you think of g as being like a linear index function, that those parameters are not important by themselves. They're not interesting in and of themselves. They don't tell us anything that we want to know. You may or may not agree with that position, but the people who do agree with that position say that what they want instead are not these index functions, but the average treatment effect. Right? And so Angerst and Pischke make a very, they argue that case strongly. Jeff Wolders has been arguing about that. He's been making that point in his textbooks for a long time. And using this method, you can address that criticism in a pretty straightforward way. So suppose in this model that we want to look at finding sharp identified sets for the average treatment effect. How would you do that? Well, let me define the average treatment effect as being the average treatment effect of going from some x star to some x double star. These don't have to be points in the support of x. Usually in the program evaluation literature, they're thought of as being points in the support of x. But if you were in an I/O application, you might care about predicting product share for a product that doesn't exist yet, that's some combination of x's, so it doesn't have to be in the support of x. It's not an important part of this. And then we define the average structural function star and double star as being the probability that you would get 1 if your x were exogenously set to x star or x double star, respectively. Okay, notice that these average structural functions are still linear functions of f. Right? That's important for making this work. And then let's define the average treatment effect as being the difference in these two average structural functions. How would you characterize a sharp identified set for the average treatment effect? Well, you'd fix a g again, an admissible g. You'd add these 2 points that we need to evaluate f at to the set script u. So now this set has had negative infinity, positive infinity, g of x, and then now it's g of x star and g of x double star, so there's 5 points. And then you just optimize. You min and max the average treatment effect over f bar for a fixed g, with f bar subject to the constraints we had on the previous slide for it being a proper subdistribution that satisfies the observational equivalence condition and then maybe like a median zero condition. Okay. This is still a linear programming problem because the average structural functions and hence the average treatment effect are going to be linear in f bar when I replace f by f bar here. Okay. So it's still easy to do. If we define the min and max values by p lower and p upper star of g, and you can show that the sharp identified set for the average treatment effect is just the union of all these intervals. Okay, and that's not super hard to show, but maybe a couple extra steps are missing here. And then what's the punchline? So now we have Mansky's assumptions of a semi-parametric binary response model, which are, I think, widely viewed to be attractive assumptions that you would like to entertain. They allow for heteroscedasticity in the error term, things of this nature. They don't make any distributional assumptions on the error. What's the main criticism of those approaches? The main criticism is, well, you can only get the structural index function at best and not the average treatment effect. So now I've addressed that criticism because now you can get the sharp identified set for the average treatment effect here as well as the index functions if you want. You may not like the identified set that you get, but that's a separate issue, right? Here's what the identified set is, and now you know how to get it. Okay? If you think it's too big for your purposes, then that's a different discussion. Okay. So let me talk a little bit about extra properties of this argument. Yeah? Yeah.
There is an identification.
Which paper did you say? Athia Nimbens?
Yes.
Yeah.
There's this identification argument for basically a discrete choice in a diffuse time design. where they show that under a very broad set of circumstances, the presumed effect is bounded, but it always well if basically it includes zero.
Mm-hmm.
How kind of good are these bounds here?
Well, these are the best bounds you can get under the assumptions.
Yeah, but are they going to be typically informative? A sign of the effect or things like that, or can you characterize it a little bit more when? Because at least one thing we want to know is the sign of the effect.
Yeah.
And in their context, I mean, it's a different diff design, but of course it's included in what you're doing. And they show that, for example, the aggregate trends are going in the same direction as the Friedman effect, then the bounds actually include zero, which is not very attractive.
Yeah, so I can't speak to the Athey and Inman's paper because I haven't read it for a long time, so I don't remember exactly what's in it. I can tell you that, are these bounds small enough? Well, they're the best you can get under these assumptions, right? That's what the sharpness means, right? These are the best you can get.
I'm not disputing that. I'm just asking informatively.
Yeah.
They can characterize when they're going to be informative.
That's an empirical matter, right?
No, because they show it's an identification question.
So whether they're small enough for your purposes is an empirical matter. Now, whether they always have some characteristic as like excluding zero or containing zero or something like that, that's the weakness of this type of approach because this is a computational approach. This is a generalized computational approach, and so it's very difficult to, you're not going to have like an analytic form for what the bounds are. And because of that, it's hard to come up with conditions that say like, oh, well, zero is going to not be in the identified set under this condition or not, or it will be under that condition or whatever. So that's a weakness of this type of approach. Now, I would argue in response to that when I show you what the identified sets look like, I mean, you could sit here for 30 minutes and try and figure out an analytic form of how you could like just characterize them in my DGP that I gave you in the simulation. They're very complicated. So I don't think that type of analytic argument is going to go very far in the type of models that we want to look at in the future because once you get to complicated models, the structure of these identified sets becomes so strange that it's very hard to actually analytically characterize them. But it's definitely a weakness to this type of approach versus like a Mansky style approach, right? Where you can frequently get some insight as to what is going to drive the width of the bounds that's lacking here. Yeah.
Your motivating example was like this bivariate probit model,
Yeah.
which is exactly shaped in Wittlichon and studied by Chiburz. So, I mean,
Wait.
Question, what?
You didn't have any parametric restriction in your model.
That's true. We didn't have
That makes things really hard, Ed. This is my advisor trying to...
the Chiburz extending my work with the same.
Yeah, so he has independence. Does it under some very specific assumptions, such as independence of the error with the outcome without the median zero assumption, right? So that rules out things like heteroscedasticity that you'd want to do.
So that's how you're extending my previous work.
Well, so first of all, this is a much more general argument. I can do this in ordered choice. I can do this in Roy models. I can do this in a variety of different types of models that are not covered in your paper. I'm just showing you the binary response model because I'm trying to keep things simple for the presentation, keep the notation simple. As well, I can add on symmetry, I can add on independence, I can do all these various things. In your paper with the Zeme, so my advisor and my friend, wow, amazing. They too. So in your paper with the Zeme, you don't have any parametric linear index structure which is really hard to do, Ed. I mean, that's the whole game here, right? Is having a semi-parametric model versus a fully non-parametric model. And your bounds aren't sharp either, by the way. They're sharp under restrictive assumptions, which Ismail Murifi showed are very restrictive.
Chiburz shows how to remove that. And Chiburz does the linear index too. So
Yeah, so there's relations. So I think Chiburz, you can kind of, yeah. So this is sort of, there's some overlap between what Chiburz did and what I'm doing, but the method is different. And the generality of what I'm doing is much broader.
So there'll be other models not covered by the previous literature, which you'll be able to cover.
Yeah, like I said, I'm just doing the binary response model because that's the easiest one to show. In the paper, I actually do an ordered choice model instead. And the same conclusions generally run through, but the notation is a little more complicated, so that's why I'm not talking about it. So there's some interesting properties of this argument, which, let's see how many I can talk about. So one thing you might be saying is, well, this linear programming characterization is for a fixed G. So linear programming is nice and easy to do, but you have to fix G first, and so you have to search over all G's somehow, which can be difficult. Even if you parameterize G to be finite dimensional, you still have to search over a grid of the dimension of what beta is. Maybe beta is 10, you have 10 covariates. That's going to be quite difficult to do. This is a limitation that's shared by a huge amount of work in partial identification, at least the computational approaches. A lot of the inferential work is hamstrung by this. This argument actually gives you an interesting way to address that. So if I show you the linear system that I'm talking about again, observe that the structural function G only enters it through the indexes that it defines for U, right? The variables are f bar. They're indexed by U, and the labels we assign to the indexes are determined by G. Okay? So essentially, G only affects the labels. Now, the labels are important. They have both ordinal and cardinal meanings. In particular, whether one is bigger than another is important. But for many different values of this G function, the labels are going to be essentially the same. So changing G is only going to be a matter of affecting the labels, right? And so I formalize this more in the paper, but essentially, if you have two values of this function G, say G and G prime, that induce the same ordering on this labeling set, then you know that G is going to be an identified set if and only if G star is an identified set. Why is that important? Well, it means that once you've created this sort of equivalence class of functions that induce the same ordering, you only have to solve once in that equivalence class. Right? So that can drastically reduce the computational burden of searching over a space of dimension beta. And if I get to the simulations, I'll show you some pictures which will make that more clear. So another thing that, well, let's see. So now I can't remember exactly when we'll show this, but now we're looking at a bivariate binary response model. So what's different here? Well, not a hell of a lot. I added on a second equation. So there's a U2, and there's two unobservables. Essentially, the argument will be similar. So I write down the observational equivalence conditions and impose constraints and constraints we want to impose on the f function, and decide what parameters we want to evaluate and things of this nature, and define the U set properly for that. And we're going to try and find subdistributions that satisfy these conditions, but the difference is that now these objects, these subdistributions, are two-dimensional objects instead of one-dimensional objects. And so that's going to complicate things not at all, but it'll complicate the math a little bit. Okay, so why does it not complicate things at all? Let me show you what a subdistribution is in two dimensions. It's a function that you will recognize as a distribution function, with the important thing being that instead of being one increasing like it was in one dimensions, now it's two increasing. Okay, what does two increasing mean? It means the f volume of this box is bigger than or equal to 0 for all these boxes. The f volume is like, I should have made a picture of this, but you take this point, subtract off this point, subtract off this point, and add off this point, you get a box. The volume that f would apply to that box has to be positive, just like you would think a probability is, right? So a subdistribution then is just going to be a function with these shape properties, which are the same shape properties as a distribution function, but it's defined only on a proper subset of the two-dimensional extended real line. And that proper subset, by the way, should have this rectangular form, which not super important, but right. Again, if that subset is defined on as the entire extended real line, then it's a distribution function in the normal sense that we think of. Okay? The important thing to notice about this extension to two dimensions, or to three dimensions or four dimensions, and why I think this approach is so powerful and so easy to extend, is that these are still linear restrictions, right? 1 and 2 are obvious. The 2 increasing you can see here is still a linear constraint. So everything remains in a linear programming paradigm, right? Which means that things are still easy to solve. Okay. So there's a lemma that says that, so this is new to this paper. You'll see it's not super hard, but it is built off of copula theory. So the lemma says that any subdistribution can be extended to a proper distribution function. In fact, this is true for a subdistribution of any dimension. In that case, you have to replace f by you have to replace this 2 increasing condition by an L increasing condition, which becomes complicated, but it extends and it's still a linear condition. How does the proof work? Maybe you fly through it real fast. It's just an outline. You have a subdistribution function. You can pull off two one-dimensional subdistribution functions by just looking at the margins of the subdistribution. You can then extend these two one-dimensional functions by interpolating. Here's that graph again. That's easy. A little less obvious is that the subdistribution function also defines a subcopula. So here's how it defines a subcopula. And then Sklar, Abe Sklar, who's an important mathematician who's actually at IIT, about 20 blocks north of here, showed that any subcopula can be extended to a proper copula. So if you use his result, you can extend this subcopula to a proper copula. You could extend these subdistributions to proper distributions. You recombine them together, and you get a distribution function that extends the subdistribution f bar. Okay, so that's the outline of how the proof works. If you wanted to put it again back into the linear system for the bivariate model, it would look exactly like this. The only difference really is you have more observational equivalence conditions. They're a little more complicated in this model. The subdistribution property is now 2 increasing instead of 1 increasing. And maybe you want to put median 0 on both errors separately. You could do other stuff. You could add independence. You could add whatever you want. Okay? Not whatever you want, but a lot of things that you want. Okay, so I have some simulations. I don't think I'll be able to go through them that well, but so the simulations are for a bivariate binary response model. There's some stuff. We're assuming that the errors are normal, so like the easiest possible case that you'd think of, it's not pathological. And so let me just, instead of going through this in detail, I'll do 2 things. One, I'll respond to Costas's complaint that I'm not getting analytic forms of these and show you that the shapes that you get are really complicated, so that coming up with the analytic forms will be very, very difficult. And then 2, I'll show you this partitioning property. So here's the identified set under various different types of assumptions. This is just the Mansky one. I can increase the size of the support, do various things like this, add on independence. I can now assume that I can relax the assumption that the endogenous variable is actually exogenous and treat it as being endogenous. And so now you get a much bigger identified set. You get strange things that happen like disconnected sets. That's weird. That's difficult to characterize. Here's a graph that shows you the partitioning property. So essentially, in each of these colored regions, you know that all that changes when you change the index beta naught or beta 1 is the labeling. And so I don't have to resolve the problem if I don't want to resolve the problem. So that's a good way to attack the curse of dimensionality. And as I start getting more and more weird assumptions, like they're not really that weird in economic terms, but you get strange sets resulting from this, right? So now I have a first stage equation, and I have independence of both the first stage and second stage errors of all the exogenous variables. And I've got this strange non-convex set, which if we sat down together and tried to, write down what the curves were here, we would have, maybe take us 5-10 minutes or something to do that, right? And so the idea of doing that analytically for any possible distribution of unobservables seems to me to be too difficult to pursue as a general research agenda. I'm happy to be proved wrong with that, but I think if you look at the literature on partial identification, you're going to agree with me. All right, and here's if I add symmetry. So now what do I have here? I mean, this is the identified set for a model that is basically like the Heckman 78 bivariate probit. The only thing that I don't have anymore is normality on the error terms. I still have symmetry around 0, I have independence, and this is what I get. Okay? Throughout all these simulations, you can get the average treatment effect. It's very easy, and then everything is sharp. All right. So let me just tell you what else is in the paper. I do this more generally for high-dimensional unobservables. I talk about these related concepts which are useful. I show you can put this into a conditional moment inequality framework. Now that's kind of cheap because it would be very difficult to apply it directly, so I'm still working on ways to make that easier, to apply the known theory of how you do inference in these models to this particular type of argument. I discussed the pros and cons of this type of general partial identification argument relative to other methods. I show you there's a Roy model example in the paper, so another example that Ed's paper can't cover. All right. Let's see how it works. All right, and this example is one where you have 3 unobservables, so you'd have a 3-dimensional subdistribution. Okay, so the conclusion, I showed you a identification argument, a new one called partial identification by extending subdistributions. It's an argument for obtaining sharp characterizations of the identified set that are tractable, meaning that they can be solved through simple computational methods, like linear programming methods. And I think it's especially useful for semi-parametric nonlinear models. The reason it's difficult to find sharp identified sets in these models is because of the added structure that the sort of parametric component, like the linear index, adds to things. and I want to still be able to exploit the linear in parameters type of structure, because I feel that if we go to a fully non-parametric framework, well, I might as well pack up and go home as far as being able to do inference to the level that users want of it. Okay. And here's some current and future work. Essentially, I'm working on applications in both of the theoretical and empirical form, and sort of extensions of the theory. And the last slide just says thanks. Sorry, I went over.
Thanks. Okay, well, first I'd definitely like to thank the organizer for inviting me to participate, even at the last minute. But seriously, so I'm going to come at things very serious. I was very pleased to hear Stefan's introductory remarks about the interaction between econometric theory and empirical work. I'm coming at this very much as a consumer of these kinds of papers and certainly a big fan. And the reason that I am such a big fan is because I think partial identification is the best chance, given where we are now in economics, of putting economics back into econometrics. In that sense, and the point being is that the typical objection to most of this stuff in empirical work is that if you want to get the economic magnitude of interest, you're going to impose these, I would call very politely, difficult to defend distributional assumptions or functional form assumptions. And what I think partial identification does is really allow you, it gives us a way to effectively be honest with ourselves, as well as also only impose the assumptions that we think are really credible. And certainly, as I said, the advantage here is that we only impose those assumptions on the unobservables and functional forms for the model that I find credible. The disadvantage, as I think Alex talked quite a bit about, is that we get up with just the identified set that contains this true magnitude of interest. It can be extremely challenging to compute an estimate of this identified set, and I think a lot of progress has been made on that. And then the next part is that what we're really interested in is inference, and inference is quite complicated. Or in other words, you can't do it in stata. And as I'm sure you all know, that's all that ever gets used. If it's not in stata, it doesn't get used. So these are really the challenges to getting these things to happen. And so the general framework of what he considers is essentially this, what he calls the partial identification by extending distribution. And this is the sort of abstract version of what he's talking about. And which I think really is a nice way of thinking, very abstract but nice way of thinking about it, of saying, look, what I'm going to do is make assumptions about the unobservable and essentially if you like, the function that links the unobservables and the conditioning variables to the observed endogenous variables, such that essentially I can recover the H and F from the conditional distribution of y given x. And then he says, okay, these are called the admissible values H and F. And then he says, okay, if H is in the identified set, if and only if there exists an admissible S that generates this. And he applies, what he comes up with is this idea of what he calls a subdistribution function that, and I think the picture that he had should certainly go in the paper, because I think that's a really nice way of essentially just for the people without the ability to think in hyperspace to envision what he really means by a subdistribution function. And essentially this is the main theoretical result that essentially says, look, fix a potential H. If you can find this subdistribution function on this restricted space that's indexed by the X and the H that satisfies the observational equivalence condition, then essentially you can extend that to the distribution f of u of x that yields the observed distribution of y. But the thing that I think is really the nice part about the paper is the fact that as he emphasizes, this linear constraints. And this gives the ability to essentially solve these things as solutions to nonlinear programs, which again gets into the thing that the empirical folks like me certainly are going to like. And so Ed's back, Ed's not back, Ed is back. So this is the ordered discrete response model that that he looked at. And I think the cases that he considered are essentially when x and mu are independent, median of x given x is 0, and then x is symmetric. Considered these same cases with the endogenous. And I think this was really, if you like, for me, the sort of the meat of the contribution of the paper that unfortunately got the last 5 minutes of his presentation. But going through and seeing how each of these different assumptions changed the identified set, I thought was certainly something that deserved a lot more discussion, particularly as really coming on to the comments that I have about it. And then finally, what he did talk about was the ability to get different from the typical sort of procedure of using his framework to get essentially the average structural function, and then to be able to estimate the average treatment effect in these sort of binary response models. So what are my comments? So my general comment, as I said here, is really about the partial identification in general. And just my plea to the folks that do this stuff is there is a latent demand for what you do. Trust me. But you got to make it accessible. You got to make it easy for us to essentially convince others of the usefulness of this procedure. So the simple thing is to say, are there simple examples to illustrate how the use and estimation can be to an important empirical question? I think the nice thing that I would very much encourage Alex to do is take a very serious empirical question and essentially show us, if you're back to here, sort of the bite of these assumptions here, as well as the parametric distribution assumption in terms of what happens to the identified set, what happens to the economic implications. In other words, what sorts of economic implications could be credibly derived from the identified set if all you're willing to assume, say, is the median of u given x is 0 in this example, versus the assumption that it's, as he said in his talk, that it's a normal, joint normal distribution in the case that it was the endogenous bivariate probit model in the case of the. So it really, that would be very, very helpful. The other is that a little bit more detail certainly on how you would actually implement this. So for example, things like, are there, even just talking about what's the software that you might use and detailed instructions. Remember, I always like to think of it as the smart graduate student test, which is, could you give your paper to a smart graduate student, and could they replicate every figure and table in your paper? I know I couldn't, sorry. So I think that would be very helpful. And then finally, I think this idea of these, of really sort of realistic Monte Carlo studies, that's what's going to convince, if you like, the sort of unwashed masses that I think, I really hope that you will reach with this literature, because as I said, it really offers a way for economic theory to really get back into econometrics, which is certainly something that I'm a huge fan of. So the specific comments now about the paper, they're mostly just really things of, tell me more. In particular, I think there's some really nice stuff that gets at Costas's question, where what he has in table 2 is when he's considering the bivariate probit model. I hate to keep saying that, the bivariate discrete response model, I guess would be the better way to say it, with endogenous right-hand side variable. He gets disconnected identified sets for the average treatment effect. Some discussion of why that's the case, what sorts of assumptions kill that off, what sorts of assumptions bring that back in. The other thing I saw is that it would also switch the sign. These are the sorts of things would be very interesting to empirical people to understand, okay, what sorts of things should I be concerned about when I'm making these assumptions in order for me to say, oh, the sign really could switch because of the fact that I made this assumption. So the final point was there was lots of promise about what specific classes of models this linear programming approach could be applied to. In the paper, he talked about the bivariate discrete response as well as the ordered discrete response. But it would be really good to see, because I think, as I said, the linear programming approach really has a lot of appeal in terms of being able to compute that. And then finally, the other one is that everything had to do with the linear function. How much headway can you get with making an arbitrary nonlinear function in X? Simply because I just, thinking back to Amemia's survey article where he essentially drives these relationships, to me, I think in the binary response models, the bigger concern is really is the index function probably less than the specific distributional assumption that I'm making on that additive error. But as I said, concluding comments is just give us more, please help us to push this product out to the wider audience of empirical people, because I really think this stuff has got a lot of promise. And as I said, as I wrote right up there, and I will continue to say, put the economics back into econometrics, and this is the way to do it. So thanks very much.